Let's talk about data distributions. In statistics, we focus so much on the normal distribution because that's what we like to use for hypothesis testing. What about the actual data points? I mean, like the distribution of the measures made, the values you could have in an Excel spreadsheet. Full truth, each field has their favorite distributions they tend to focus on, so not everybody will agree. But I find in biomedical and public health research, the normal distribution can be hard to justify. In this video, we'll talk about how to identify a probability distribution that is actually relevant to the data you're collecting. When thinking about possible distributions, I usually start with the support. What's the support? It just means the range of values that are possible for a distribution. If we made a histogram of the data, like this one, the x-axis represents each value observed in the data, and the y-axis represents which values were more or less common, with the vertical bars helping us to visually represent which ranges are more typical or less typical. The support gets at what range of values on the x-axis could ever be demonstrated in the data. Probabilities aside, are there some values which are just straight up impossible, could never be demonstrated in the data just because of the way you are collecting data? For example, consider a binary variable. For a binary measure, there are only two possible outcomes. Event occurs or it does not occur. To put it in more mathematical terms, the support is the set of 0 and 1. Either the event does not occur, denoted by 0, or it does occur, denoted by 1. Binary data are usually pretty obvious. The support is more helpful for continuous data. In most biomedical applications, there usually are limits to the measures we're making. If you count the number of infections at the hospital, you can't have a negative number of counts. It doesn't make sense. If we sketch out a histogram of count data like this one, there's no world where the x-axis goes left of 0. Alternatively, if you ask participants how many days in the past month they smoked, you cannot have more than 31 days reported, like in this histogram where the x-axis has to stop at 31. Lastly, a lab machine may not be able to detect concentrations under a certain threshold, depending on how precise it is. Being aware of this, it helps us understand what values could ever be observed in the primary data. In this case, the true distribution of the biomarker may extend to 0, but we'll need to nudge the x-axis to the left a little bit to account for the impossibility that the device will measure a very small concentration. Another consideration you can think about is whether or not data reflect a true continuum or are better understood as counts. A count distribution will only provide raw data points that are whole numbers, no decimals. There could be counts of 0, 1, 2, and so on, but nothing in between. A continuous distribution, on the other hand, can be any rational number with as many decimal places as you like. Once we've worked out the scope of actual values you could obtain, we'll also need to think about what values are more or less likely to be observed. The distribution itself, which vertical bars on the histogram are going to be taller or shorter. I tend to focus on two aspects: the variance, which is the range of most likely values, and symmetry, called skew. Are you expecting data to have a lot of variation, like the histogram with vertical bars well spread out along the x-axis? Or are the data pretty close together most of the time, like this histogram, where most of the vertical bars are clustered in the middle? For the variation we do see, will it be pretty evenly spread across the range of possible values, like this rectangular histogram? Or are they bunched up at one end, like this histogram, where most of the data are low values with a few values that are really high? Keeping these qualities in mind, you can start mapping out what you anticipate from the data you collect to candidate probability distributions. We'll talk about each one in more detail, but I tend to focus on one of the following: binomial, Poisson, negative binomial, exponential, or gamma. Before we get into that, I know it can be hard to watch a long video, so if you need a short intermission, this would be a good time to go check your email, or if you work from home like me, it might be time to check the laundry. All right, let's talk specific distributions. The binomial distribution represents data that are black and white. Either the event occurs or it does not occur. We often denote the event not occurring with a value of 0 and the event occurring with the value of 1. Binomial data are easy to spot because the support is limited to these two possible outcomes with a probability parameter reflecting the likelihood of event. Here's a histogram of binomial data with only two vertical bars at 0 and 1, corresponding to the number of times the event did not occur and the number of times they did occur. Examples include a patient being in remission, a patient being infected, or a patient discharging within a certain time frame. The Poisson distribution is a count distribution. Examples of count data include the number of symptoms a patient reports, the number of times a patient sees their doctor. Here's a histogram for Poisson random data. As represented by the x-axis starting at 0, the support cannot be less than 0 because it is impossible to have negative counts. However, on the other extreme, it is possible the counts can be very high, as demonstrated by the x-axis going to 10. A Poisson distribution has a single rate parameter that corresponds to the average as well as the variance. If the average is close to 0, because the support cannot go below 0, then there will be some skew in the data with many 0 counts or counts of 1, and a handful of counts that are higher, like 2, 3, or 4. This histogram represents the skew of a Poisson distribution with a low rate parameter. Most of the vertical bars are tall and on the left side of the chart, close to 0. Conversely, as the parameter increases, the average gets further from 0 and the skew disappears. It starts to look more symmetrical, like a normal distribution, as in this histogram, where most of the vertical bars are tall and in the middle, with shorter bars on both the left and right sides. Additionally, because the Poisson distribution is a one parameter distribution, as the average increases, so too does the variance increase, because there's now a wider range of values that could be observed due to the average being further from 0. An alternative count distribution is the negative binomial distribution. In some conditions, negative binomial data will look the same as a Poisson distribution. However, there are two parameters for the negative binomial distribution, which allows for more flexibility. This means you can see more skew with negative binomial data than you see in a Poisson distribution, even if the average is higher. Here's an example histogram of a negative binomial distribution where the average is not close to 0. The average is closer to 5. Yet there still is skew in the data. Most of the vertical bars close to 3 or 4, and some vertical bars as high numbers like 9 or 10. Additionally, a negative binomial distribution, the variance is no longer implied by the average. So there's more flexibility in the range of possible values you see. The negative binomial distribution is often characterized as a more dispersed version of a Poisson distribution because there can be more skew and higher variance regardless of where the average is. If you have continuous data rather than counts, I tend to think about these as either exponential or gamma distributions. And like before, it is the range of likely values and skew that helps us decide which is most plausible. Examples of continuous data include the amount of time a patient waits for an appointment, or the volume of a biomarker. In both cases, negative numbers are impossible. There cannot be a negative amount of time or a negative volume. That said, unlike count data, decimal values are possible for continuous data. You cannot pick up 1.5 prescriptions from a pharmacy. However, the volume of prescription itself could be in any fractional amount. An exponential distribution has a very characteristic shape, represented by this histogram. Most of the values for an exponential distribution are very close to 0, represented by the vertical bars on the far left of the chart. Higher values show a consistently decreasing likelihood of observation in exponential data. Shorter bars as we go further to the right on the chart. There is one rate parameter in exponential data, which corresponds to the inverse of the average. Additionally, the average is equal to the standard deviation. So like a Poisson distribution, as the average increases, so too is the implied variance. Importantly, regardless of rate parameter or average, the characteristic skew is the same for all exponential data. Specifically, all exponential distributions have 2 skew and 6 kurtosis, the fourth central moment of data, which represents heaviness of tails. It just means that the same steady decreasing probabilities of high values are anticipated for any exponential distribution, no matter how high or low the average is. Here's a histogram for an exponential random variable with mean 10. This histogram on the right is an exponential random variable with mean 100. Despite a tenfold increase in the average, the silhouette of each histogram is essentially the same, with most vertical bars on the left close to zero and trailing off as you get further to the right. A more flexible continuous distribution is the gamma distribution. This distribution is a generalization of the exponential distribution, which allows the anticipated skew to vary, changing what the distribution itself will look like. It has two parameters, which means it can show the same skew as an exponential distribution, like in this histogram where most of the vertical bars are on the left and you have some shorter bars as you move to the right. Gamma distributions can also have less skew, more like a symmetrical normal distribution, as in this histogram where most of the vertical bars are squarely in the middle, with even numbers of short bars on the left and right sides. The variance of a gamma distribution is also more distinguished from the average because it is more flexible in what values are more or less probable. These are the main distributions I think about for real world biomedical data. To recap, that's how I go about matching a distribution to data. First, I think about what values are possible or likely. If the data are binary, occurs or does not occur, that's an easy one. It must be binomial distribution. If it's a continuous distribution, think about what a histogram of the data would look like. What is the average and what range of values would you expect? Do you think there will be skew, or is it fairly symmetrical around the average? Are we expecting whole number counts, or are decimals possible? If it's count data, I usually go with Poisson or negative binomial. Poisson for relatively simple counts, negative binomial for counts that could show some extremely high values occasionally. So to say, more skew and higher variance. If it's continuous, I usually go with exponential or gamma. Exponential if you expect most of the data to be very close to zero. Gamma if you think the data are more spread out, with a skewed average that is further from zero, or even no skew at all. If you're still not sure, you can always simulate data from these distributions to see how they come out. You can use the method of moments estimators, whereby you choose the value of the mean, variance, or skew statistics and infer what parameter values are implied. For example, say you have a biomarker for which most patients have a value around 8 or slightly less, but there's extensive skew, such that some people have really high levels. If that is the case, a gamma distribution would be a good fit. If you want extreme skew, a value of 10 for skewness would be extreme. You can buy a book on probability theory, but honestly, Wikipedia has pretty good basic information on data distributions. The skewness of a gamma distribution is equal to 2 divided by the square root of the shape parameter alpha. So if we want 10 skew, we can solve this equation for alpha, giving us the quantity of 2 divided by the chosen skewness, quantity squared, or 1 over 25 in this case. The average for a gamma distribution is simply the product of the shape and scale parameters alpha and beta. If we know this shape parameter alpha is equal to 1/25th, to have an average of 8, the scale parameter beta must be 8 times 25 or 200. This is one example of how to work it out. If algebra isn't your favorite, Guess and Check may take some trial and error, but it works. You can try out different values of the parameters until the distribution starts to look right. Choose some parameters as a starting point. Simulate some data. Create a histogram of those simulated data points and see if the raw data you get look like the values you could plausibly obtain. Did you get whole numbers when you were expecting decimals? Did you get negative numbers? Did the presence or absence of skew match what you were expecting? If not, you may need to change the parameters used or the distribution chosen if they're really out of sync.